So with that note, I give you my colleague, Keith Conrad, is going to talk about stuff.
Yeah, so let's talk about some stuff with the letter L. Okay, so there's some notes that I wrote. I'll be updating. I think they go up through maybe the first 2 or 3 lectures. I'll send them to Alvaro. He can post them on the website later today. So I want to talk about what are called L-functions and the famous Riemann hypothesis, or generalized Riemann hypothesis. So I think...
One thing, sorry.
Yes.
So some of us, later tonight, myself, I can't be here tonight, but some of us, namely Keith, will be around in the...
So after dinner, I'll come back here to see if anybody's here. You can come back here. The building is unlocked until 7 p.m. And so if you get back before 7, you can meet in this room or the room across the way, if the air conditioning is on, or out in the lounge area where the air conditioning was always quite nice while you guys were boiling in here. Before, I was out there very comfortably sitting. Anyway, so I'll be back, and so if you have questions about stuff, if you're working on exercises, you can answer them. Okay, so right. So I think for most of today, I'm going to give a kind of a survey of where the zeta function came from, the most classical, most basic example of an L function, why people were interested in it, its connection to primes, and what we think we might be able to do with it, and why this Riemann hypothesis is so important. The number theorists have certainly done a very good job in PR in convincing everybody in math that this is the most important problem in math. So I'm not going to object to that claim. But as we'll see, it's not really because of the Riemann hypothesis for this one zeta function. There's merely a broader reason. But in any case, so let's begin. So our story sort of starts with Euler in the 1700s. And so for a real number s bigger than 1, he considered the infinite series of the reciprocal powers. So you have your 1 plus 1 over 2 to the s plus 1 over 3 to the s, and so on. And what he realized was that this is actually expressible as an infinite product over the prime numbers. 1 over 1 minus 1 over p to the s. A lot of reciprocals there. And the idea is if you were to expand out the right-hand side and each factor into a geometric series, 1 plus 1 over p to the s plus 1 over p to the 2s. So here we can product over p, 1 plus 1 over p to the s plus 1 over p to the 2s, and so on. And if you multiplied out these series, these geometric series over all the different primes, thanks to unique factorization, you're going to get a reciprocal s power of every positive integer exactly once. In fact, you could consider this identity to be literally equivalent to the statement of unique factorization in the integers. Oh, it's a very analytic statement. In any case, so Euler essentially discovered this decomposition. He would then go ahead and use it with negative s, where the things don't make any sense, but he's Euler, so he can get useful results out of it. One thing that he observed, that he extracted from this identity, was the fact that as you let s go to 1, this series blows up intuitively. If you set s equal to 1, the series becomes the harmonic series, which blows up. Of course, there's still some error estimate to show that means the series to the right of 1 actually gets big as s gets close to 1, but one can do such things. But since that blows up, on the right-hand side, the product cannot have a finite number of factors, because the right-hand side, every individual factor converges as s goes to 1. And so if the whole thing blows up, then there must be an infinite number of factors, and so this must imply that we have infinitely many prime numbers. So this was Euler's proof that there were infinitely many primes. In some sense, in calculus, the divergence of the harmonic series, doesn't sound like it has anything to do with prime numbers, implies the infinitude of the primes. And Euler went on and he would take the logarithm, because you have a product representation, you can take the logarithm of the series. You don't want to actually directly take the logarithm of that series. Is the writing okay for you in the back? Yeah, thanks. So you can't take the logarithm of the series directly. It looks like it'd be a big mess, but the log of a product is the sum of the logs. And if you remember calculus, log of 1 over 1 minus something, anyway, if you do the math, You get an infinite series over the primes and the positive integers, which we can collect into a sum over the prime powers, 1 over kp to the ks. So we have a representation of, no, I don't need a minus sign because it's 1 over 1 minus x, and the log of that is minus the log of 1 minus x, which is the sum of x to the k over k. Everything's okay. I hope I don't need a minus sign because the left-hand side is definitely positive. So everything is fine. In any case, so the Euler product allows us to write the logarithm as a series, and then from this, Euler was able to deduce that the sum of the reciprocal primes is infinite. So there are enough primes that the reciprocals have a divergent sum, unlike, say, the squares. So in any case, so he's able to get some information about the primes from this product representation. So this thing here, this is called the Euler product. Okay, but the whole time he's working with real numbers. All right. So if we go ahead around the year 1800, as Alvaro mentioned in his talk, Gauss, Legendre, and others were led by data to conjecture the prime number theorem. Okay, so the next step in our story concerns the count of primes. So let pi of x, the number of primes. I'll always write p for a prime, the number of primes up to x. And so in the, 1790s, independently, Gauss and Legendre conjectured that the number of primes up to x grows like x over log x. The ratio tends to 1. Okay, so I don't know what you were doing when you were 14 or 15, but Gauss was counting thousands of prime numbers and spending his time wisely that way. And then Legendre came across essentially the same conjecture, an equivalent version that was mentioned earlier, going back, well, if Wikipedia can be trusted, going back to Dirichlet. I actually didn't realize that. I thought this integral version was due to Gauss. The integral and the x over log x, if you do an integration by parts, you can see that x over log x is like the biggest piece of the integral. In any case, so both of these, the equivalents of the two expressions, they definitely grow at the same rate, but the fact that the count of primes grows like them, this was the hard problem. And so there really wasn't much progress on this until the mid-19th century. And so in the 1840s and 1850s, Chebyshev comes along, and he used this series to show, well, first of all, that the count of the primes was on the order of x over log x in a quantitative way, something like 1.1 and 0.92 x over log x. Okay, at least for big enough x big, greater than 0. And so it was kind of the right order of magnitude, and he was even able to show that if the ratio of pi of x to x over log x tended to a limit, that limit has to be 1. That does not prove the prime number theorem because it is totally non-obvious that the ratio has a limit. But at least that shows us that up to constants, it's the right expression to be aiming for. But again, he used the zeta function for real numbers s, and he introduced some auxiliary functions to help out, which turned out, for completely different reasons, to be very helpful in other ways. And so then things kind of stood still for about 10 years. And so this was like the 1840s, 1850s, early 1850s when Chebyshev did this. And then finally in 1859, Riemann comes along, and he was the first person to consider this series with S being a complex variable. Okay, so and he even introduced the standard notation. So he would now consider for a complex number S with real part bigger than 1, we have the zeta function. So your first exercise is to figure out how to draw the letter zeta without making it look like just a random squiggle. Okay? So, I mean, I've met experts in number theory who cannot deal with this task, but just sit down and figure it out. Okay, Greek children can do this. You should be able to do it too. Okay, so in any case, by using absolute values, he realized that, well, of course, the sum converges absolutely with complex s to the right of 1 in the real part, and the product representation is still legitimate. Okay? Well, for someone like Riemann, this is pretty obvious. In any case, so what do you gain by thinking about this for complex numbers? See, the difference between the complex plane and the real line is if you have a bad point for your function in the complex plane, you could go around it. Right? On the real line, if something blows up, there's no connection to what's on the other side. But, if this function blows up at 1, I can just go around it and try to keep on going. And so what he realized was that he was able to show that this function, it's analytic to the right of 1. It has an analytic continuation to the entire complex plane. And, well, I say analytic, except for a simple pole at 1. Okay, it does blow up at 1 to first order. Near the number 1, it looks something like 1 over s minus 1 plus higher order terms. Okay, that's the only place where it's kind of ill-defined. Everywhere else, it's nice and analytic, has local power series expansions. And, by the way, this analytic continuation is not given by either of those other formulas. They don't make sense. It's like a geometric series, summing x to the n, doesn't make sense if x is big. But of course, if you rewrite it as 1 over 1 minus x, that makes sense. Okay? So he found a different, more complicated formula for the zeta function that actually makes sense in a nice way outside the range of numbers with real part bigger than 1. And so that's how he got the analytic continuation. It was not some abstract proof. He wrote down a formula and said, look, this makes sense. Here's the extension for it. And then he also discovered that zeta of s satisfies what's called a functional equation that relates the values at s and 1 minus s. It's not that zeta of s equals zeta of 1 minus s. That's not it. But there's a certain way you can, if you know one value, you can read off the other value. Okay? And what he did with this, the reason he was studying this was that he set up a program to prove the prime number theorem. He said, well, look, let's consider this function. I can give it a meaning to the entire complex plane. And if we could show this, and this, then the prime number theorem would kind of drop out. So, of course, until you have a proof of something, it's just a matter of judgment. Oh, that looks like a good idea. That looks like nonsense. But anyway, he set up a set of steps to try to carry out, like the 1859. And he didn't live much longer. But in particular, his ideas did work out in the end, long after he passed away. In 1896, as was mentioned in the first lecture today on arithmetic statistics, his ideas actually worked out, right? So in 1896, finally, Hadamard, and De la Vallée-Poussin actually worked out, were able to use the Riemann's ideas to prove the prime number theorem. Okay? In fact, they showed that if you could show that the zeta function a little bit to the left of 1, the other formulas don't work, but you can get the extension a little bit to the left of 1. If you can show it doesn't have any zeros, doesn't vanish, and in some range to the left of the line real part equals 1, then you could deduce the prime number theorem, and that's really what they did. Supposedly, this is basically a 100-year-old unsolved problem, right? Gauss and Legendre, 1800, we're almost in 1900. Apparently, at the time, the myth was that the people who prove it will live forever, and they almost did, right? If you looked at the years when Hadamard and De la, they almost lived to 100, so close. In any case, so what it turned out, in fact, later, the connection between the zeta function and the prime number theorem was much closer than just you could use zeta to prove the prime number theorem. Wiener, I think in the 1930s, 1932, he showed that, in fact, the prime number theorem is equivalent to the vanishing, the non-vanishing of the zeta function on the line real part equals 1. I don't mean equivalent in the sense that they're both true. prime number theorem is equivalent to 1 plus 1 equals 2 because they're both true. But if you assume one, you can get the other and vice versa. And so we have this kind of very important principle here that understanding, this is kind of, I think this was advocated by Hecke, understanding where analytic functions have their zeros and poles can really be a source of interesting number theoretic results. So I want to make one comment here concerning analytic functions. So you might get the impression, if you've never read a proof of the prime number theorem, that in order to prove the prime number theorem, you work with the zeta function. This isn't quite true. What you work with is the logarithmic derivative. So if I write log f, that's a very delicate thing in complex analysis, and I take its derivative, you would get 1 over f prime. Now that makes sense irrespective of whether it comes from a real or fictitious logarithm function. And so this is called a logarithmic derivative of the function, 1 over f prime. And a nice thing to check is if you have a function with a power series expansion around a point, c times s minus a to the n plus higher order terms around the number a, c is not 0, it's a nice exercise to check that near the number a, 1 over f prime looks like m over s minus a plus higher order stuff. Okay? In other words, the order of vanishing of the original function has turned into the residue of the logarithmic derivative. Logarithmic derivatives always have, at worst, simple poles. If m is 0, there is no pole, but if m isn't 0, there's at most a simple pole. So what you use to prove the prime number theorem is really the logarithmic derivative of the zeta function and not the zeta function directly, but the only way you can access the logarithmic derivative is through that Euler product representation. It really kind of helps you out. Okay, so let's talk about this analytic continuation of the zeta function. Are there any questions? Okay, so where do things start? So analytic continuation of the zeta function. So you could take a course on complex analysis and you can learn abstract theorems about, how far can you extend a function. But if you actually want to work out a specific example like this, you really have to use something about it. And so our story actually begins with the gamma function. So let me review a little bit about that. You might have heard about it or maybe not, but I want to recall where it comes from. So here, like many things, the story starts with Euler. Euler discovered that you can write n factorial as an improper integral, 0 to infinity, x to the n, e to the minus x dx. Okay, for n equals 0, 1, 2, and so on. Cute formula. Prove it by integration by parts and induction on n. And so related to that, much later on, mathematicians introduced the zeta function, the gamma function. For real part of s bigger than 0, we define the gamma function, gamma of s. It's going to look pretty similar. X to the s, e to the minus x, but I'm going to use dx over x. Okay? So if you want to recover, so this converges for complex numbers with real part bigger than 0. And so if you want to recover Euler's identity above, you have to plug in n plus 1 so that the plus 1 and the s will cancel with the 1 over x. So you get your gamma of n plus 1 is n factorial, which leads to endless people posting on Math Stack Exchange and Reddit asking, what do they define as gamma function? So gamma of n plus 1 is n factorial. It should be gamma of n is n factorial. Come on. So whether you feel it's a mistake or not, we're stuck with it. Anyway, so this gamma function itself, although initially defined only in a half plane to the right of 0, can be extended to the whole plane, not by that formula though. But if you use integration by parts, you can get a continuous extension of the factorial recursion, and gamma of s plus 1 is s gamma of s. So this in a special case becomes n plus 1 factorial is n plus 1 times n factorial. Okay? So with this relation, though, you see, it's like, aha. So gamma of s, I could write as gamma of s plus 1 over s. And that makes sense where the real part of s is bigger than minus 1. because now s plus 1 would have real part bigger than 0. Oh, but I can shift it over again, gamma of s plus 2 over s plus 1. And now that makes sense where the real part of s is bigger than minus 2, and so on. So you can keep pushing the domain of the gamma function further and further to the left, except you do pick up some poles. The first formula gives you a pole when s is 0. See, gamma of 1 is 1. And so the first formula, when s is 0, it blows up. The second formula, when s is minus 1, it blows up. And so on. You're going to get simple poles at 0 and the negative integers, and no zeros at all. So the gamma function does not vanish anywhere. It's totally non-obvious from the integral that define it that it doesn't vanish to the right of 0, but doesn't vanish to the right of 0, but that turns out to be the case. And by continually shifting, you get no zeros, but you do pick up poles at 0 and the negative integers, and this is going to be important when we discuss the analytic continuation of the zeta function. So when I was in college, my math classes never required a calculator, except one time on a complex analysis assignment. See, there was no internet back then. I'm a very old person. I had to, the task was to find the residue of the gamma function. No Google, find the residue of the gamma function at the 0 and the negative integers. I couldn't figure it out. So one time in my college career, I used a calculator to kind of estimate the residues until I saw the patterns. Like, aha! Once you know what you're looking for, it can help to solve the problem. All right, so how does the analytic continuation of the zeta function work? We're going to use the gamma function with the zeta function to get a nice extension, and then we're just going to divide out by the gamma function afterwards to isolate the zeta function in the end. So how does this work? So what Riemann realized, so first he had a messy proof of the analytic continuation, but once he got his result, he then realized there was a better way. So his paper had two proofs of the analytic continuation. And what he realized was we should consider, again, starting to the right of 1, what's called the completed zeta function. We're going to stick in some extra factors. We're going to augment the Euler product. We're going to put pi to the minus s over 2. That's an exponential factor, never vanishes, never has poles, times gamma of s over 2 times the zeta function. Okay? So if you want to, you could write it, the whole thing as a product with the primes. So anybody who's heard about p-adic stuff, you should think about this as the pi to the minus s over 2, gamma of s over 2 is like the real or Archimedean piece, and then you have these p-adic pieces, or pieces associated to the different primes, and they really are methods of kind of using this viewpoint to get a different technique for getting the analytic continuation that was part of what's called Tate's thesis about 100 years after Riemann in the 1950s, in 1950. But in any case, Riemann, by taking the combination of these three things, which the first time you see it looks very weird, what he was able to do is by using some techniques of Fourier analysis related to important things like the Poisson summation formula, so ... he was able to write this thing as an improper integral from 1, not 0, remember gamma started at 0, 1 to infinity of some function of s and t dt plus 1 over s plus 1 over 1 minus s. Maybe I'm making some sign errors here. In any case, the thing inside the integral sign was visibly invariant under replacing s with 1 minus s. And the two pieces at the end, 1 over s and 1 over 1 minus s, they turn into each other as well. They swap positions. And so the nature and the integral, because it starts at 1, stays away from 0, actually converges and makes sense everywhere. And so this provides the analytic continuation. This is an entire function in S, and here we get poles at 0 and 1. And so therefore, and by the symmetry, you get that the completed zeta function at S and 1 minus S are the same. And that's the functional equation. The values at S and 1 minus S are the same. You could rewrite it as zeta of S is some yucky mess times zeta of 1 minus s, but the right way to approach it is to get the clean functional equation by sticking in these extra factors, and then afterwards you divide out by it. Because if you can get an extension of pi to the minus s over 2, gamma of s over 2, zeta of s, well, then you could just redefine zeta of s as the completed guy divided by pi to the minus s over 2, gamma of s over 2. Okay? And so that's how Riemann got the analytic continuation and the functional equation. So when you're relating values at s and 1 minus s, yes, question?
Why is there no pole at 0 then? If there's a
good question. Okay, so the question is, why is there no pole at 0? So the completed zeta function has poles at 0 and 1. The ordinary Riemann zeta function only has a pole at 1. Let's actually look at that. So what we can see by this formula is that the completed guy has poles at 0 and 1. Okay? So this guy has simple poles at 0 and 1. Now, if you look at the definition of the completed guy, we would define the zeta function in its wider domain as z of s divided by pi to the minus s over 2, gamma of s over 2. So this guy has simple poles at 0 and 1. The pi piece, no zeros or poles. What about gamma of s over 2? Well, it certainly has no pole at 1, but it does have a simple pole at 0, right? Because gamma of s is going to have a pole, so s over 2 is a little constant change of variables there. And so when you take the ratio, the simple pole cancels out. Okay, good question. So you should be careful about, right, are we talking about the zeta function or the completed zeta function? So the completed guy has the nice symmetry. But if you want to write it in terms of ordinary Riemann zeta, you're still left with the pole at 1, but the pole at 0 disappeared. Are there any other questions? No? Okay. So if we take a look at the idea of s to 1 minus s, so there's 0, there's 1, there's 1/2. Okay, so if you have a point s, where is 1 minus s going to be located? So on the real line, you think, well, there's s, there's 1 minus s. But in the complex plane, they're kind of on opposite sides of a half. If that's s, 1 minus s is down here, because after all, their average is a half. And so 1/2 better lie in the middle of the line in between them. Okay? So in any case, so the number 1/2 is certainly very important relative to the line of symmetry, relative to the symmetry of the completed equation. And so here we have the famous line, real part equals a half. So this is called the critical line, and the region between 0 and 1 is called the critical strip. Okay, it's kind of where all the action is taking place. So why is this the region of great interest? You see, to the right of 1, the zeta function doesn't vanish. Right? If you go to the right of 1, let's take a look at the completed zeta function. It's pi to the minus s over 2, gamma of s over 2, zeta of s. Now, this guy is not 0 by the Euler product. I'm using air quotes there because just because you write something as a product doesn't mean it can't be 0. Take the product of 1 over n. Okay? But most people say, oh, it doesn't vanish because of the Euler product. That's sort of okay, but there's a little bit of a detail missing there. In any case, that's the idea. Morally speaking, the Euler product for the zeta function explains why it does not vanish to the right of 1. The pi guy, of course, doesn't vanish anywhere. And the gamma guy, again, I said that the gamma function has no zeros, in fact, not even any poles to the right of 0. So the whole thing doesn't vanish. So that's nice. So the completed guy is not 0 to the right of 1. But by the functional equation, we can go to the left of 0. Z of s is z of 1 minus s. And that has real part bigger than 1. And so that's not 0 either. And so if we go to the left of 0, by the functional equation, z of s doesn't vanish there either. Okay? So the only place where z of s might vanish is in the region between 0 and 1. So what does that tell us about the zeros or poles of the Riemann zeta function? So let's think about, well, we know to the right of 1, zeta doesn't vanish. Let's think about what happens to the left of the real part equals 0, the imaginary axis. The completed zeta function, if you're to the left of 0, then we know that z of s is not 0, but also gamma of s over 2 is going to have poles. This is going to have poles where? Where s over 2 is minus 1, minus 2, minus 3, minus 4, where the gamma function has its poles to the left of 0. This is going to have poles at the negative even integers because it's s over 2. So s over 2 will be minus 1, minus 2, minus 3, and so on. But look at the product. Pi to a power gamma times zeta. So if the completed guy is non-zero to the left of 0, the gamma function has a simple pole at a number in that region. The zeta function has got to have a simple 0 to cancel out and leave behind a non-vanishing expression. And so this tells us that the zeta function has simple zeros at minus 2, minus 4, minus 6. Okay? And since this is so easy to explain, they're called the trivial zeros of the zeta function. Their existence is simply a consequence of the location of the poles of the gamma of s over 2, knowing that the completed zeta function does not vanish to the left of 0. So we have a whole bunch of simple zeros for the completed, for the regular zeta function. These are not zeros of the completed guy. And so the only other place to look at is in the strip of numbers between 0 and 1. So what can we say there? Well, we know the completed guy, we saw from that formula, has a pole at 0. The gamma function, gamma of s, has a pole at 0, both simple poles. Gamma of s over 2 has a simple pole at 0. So if z of s has a simple pole, I'm looking at the thing in the upper right. If z of s has a pole when s is 0, and gamma of s over 2 has a pole, simple pole when s is 0, and the pi power doesn't contribute to that, the zeta function has got to be non-zero at that number. Because if it were 0 at the number, it would cancel out the simple pole, you'd have a problem. And if it had a pole at that number, it would be an even worse pole on the right-hand side. So in fact, it turns out, I'll just write it here, zeta of 0 actually turns out to be, I think, minus a half. Okay? The exact value is not so important for us here. But in any case, so the zeta function does not vanish at 0. It does have a pole at 1, does not vanish at 0. And I said before, from the prime number theorem, the zeta function, both of them, they don't vanish on the line 1, and so by the symmetry, essentially, they don't vanish on the line 0 either. So the only location for extra additional zeros would be strictly between 0 and 1. Okay? And so Riemann famously suggested that the additional zeros should all be on the line 1/2. Okay? So we know that there are not any zeros on the line 0 and 1, and so there we get the famous Riemann hypothesis, is the assertion that if the zeta function is 0 and the real part is between 0 and 1, well, I can put equalities, it's not going to affect anything, that you have to be on the line 1/2. So an equivalent version is that if the completed guy is 0, you have to be on the line 1/2. Forget being between 0 and 1, the completed guy doesn't have zeros elsewhere. So the non-trivial zeros, the ones that are not negative even integers, the non-trivial zeros of the zeta function are exactly the same thing as just the zeros of the completed guy with the same multiplicities. Okay, so you could say the Riemann hypothesis, as I wrote, is just simply saying all the zeros of the completed zeta function are on the line real part equals 1/2. In terms of the Riemann zeta function, all of its zeros, other than the negative even integers, are on the line real part equals 1/2. So what's known about this? So numerically, Well, first of all, the zeta function is negative for real numbers between 0 and 1. You don't have any zeros on the real line between 0 and 1. And the first few, if you look in the upper half plane, the first few zeros indeed are 1/2 plus it, where t, the first one is around 14.13, then the next one is around 21.02, the next one I think 25.01, and so on. Okay? So you have to go up a fair bit before you start to see the first zero of the zeta function. And of course, since Riemann's time, this has been massively checked numerically up to great heights, and there have been no counterexamples found. Of course, there's a natural question here. Well, I guess there are two questions. One, why do we care so much? Why is this considered the biggest important problem in mathematics to figure out? But the other thing is, how do you actually check such things? You see, if you're in calculus, find out where a function vanishes by saying, well, it's positive here and negative here, so it has to vanish somewhere in between. But here we're dealing with functions of a complex variable. Here. Well, it's complex here and complex there, so there's a zero in between. How does that work? Okay. So actually, I'm not going to go into the fine details of this, but again, the functional equation is going to help us out a lot. So how in theory would you verify the Riemann hypothesis up to some height? So I'm just thinking about the upper half plane. Because you have a zero in the upper half plane, s is here, 1 minus s is down there, and vice versa. So just to check the Riemann hypothesis in the upper half plane to some bound, and you've checked it also in the lower half plane to that bound as well. So how would you actually, how do you check the Riemann hypothesis numerically? So thing is, let's, how do I want to put this? Let's say t is real. So one can show that because the completed zeta function is real valued on the real line, that any analytic function or meromorphic function that's real valued on the real line, even the little piece of the real line, has to commute with conjugation. And so what that would tell us is, if I look on the critical line, value at 1/2 plus it, the conjugate of that is the value at the conjugate number. But now the functional equation helps out. I can write that as 1 minus 1/2 minus it. Aha! That's 1/2 plus it. Look at that. Awesome. That tells us the completed zeta function is actually real valued. So we can use calculus ideas or topology ideas. All I have to do is look for sign changes. Sign changes in this real valued function give me zeros on the critical line. Now, there's a lot more you have to do, because what if the function's values are extremely small? So maybe you have to amplify some things. But this is the basic principle is, one way you can detect zeros is if you just compute the values in some range and find a bunch of sign changes, then there has to be a zero everywhere in between. Now, if there were a double zero, you'd be screwed because it might be positive on both sides or it would be negative on both sides. You wouldn't be able to discretely isolate the existence of it so easily. Amazingly, fortunately, all the zeros that have been found so far turn out to be explained by sign changes. How do we know that? Just because I find, say, 5 sign changes up to some region, so I can find there must be a zero in between, how do I still know that that's all of them? Are we just kind of crossing our fingers and hoping? So there's a completely different way to count zeros. I don't know if anyone who's had complex analysis learned a method in complex analysis to count zeros in a box. Argument principle. So there's a nice result in complex analysis that tells us that if you had, say, a holomorphic function, is holomorphic on this region inside this strip, that if you integrate 1 over f prime around the contour, I already wrote the gamma, then this is going to be the holomorphic on here and not 0 on the boundary. So 1 over f makes sense. Then if you're going to integrate 1 over f prime, it's going to give you the number of zeros in the region with multiplicity. A double 0 would count twice. If f were meromorphic inside the region, you'd have the number of zeros minus the number of poles. The reason for, 1 over 2 pi I, right? How can you forget the 2 pi I in the complex analysis? So this is basically coming from the residue theorem. Remember I showed you the residue of 1 over f prime is the multiplicity at that point. So if you sum the residues of this thing, you're going to be summing up the multiplicities of this original function at all the points. So you're going to add up the zeros with multiplicity. So that's where that comes from. And so then what you can do, so you can count in a box, you can count zeros in a box. Here's the complex plane, there's 0, there's 1, and so you can kind of make a box going around. Of course, the completed guy has a pole at 0 and 1, the Riemann zeta function has a pole at 1, so you have to futz around a bit to get rid of that 1 or 2 poles, but ignoring that technicality, if you integrate around a box, you get a count. You get the number of zeros. And you know it's an integer. So if you get it to within 0.001, you're done, because the actual value must be an exact integer. But then you can use sign changes. So you get the number of zeros in the box. And then, separately, you use sign changes on the critical line to count zeros on the critical line. And if they match, you're done. You've proved, I know there are 5 zeros inside the region, I found enough sign changes to explain 5 zeros, and so there are no others. Okay? So in a nutshell, this is how people have verified the Riemann hypothesis up to various heights. Apparently Riemann himself, in some notes, people found that he had numerically estimated some of the initial zeros, so his conjecture was not, at the time, was not simply a wild guess. In any case, so that's how we count. That's how we count the zeros. If there were a higher order 0, if there were non-simple zeros, this method would have to be augmented in some way, but nobody's ever had to worry about how that might work, because as far as we have checked, the count of the number of sign change. A sign change doesn't tell you a multiplicity. Well, I guess it tells you an odd multiplicity. But in any case, the sum of the sign changes has always been matched by the number of zeros, and so they're all simple zeros. And so in some sense, that would be the refined, I'm just making up a term, the simple Riemann hypothesis. How about that? That all the zeros are on the critical line and they're all simple zeros. Okay? Are there any questions? Okay. So, so why do we care about the Riemann hypothesis? Get $1 million. But that was not a rationale until the year 2000, but still many people worked on it. Even if people work on it today, nobody's working on it in order to earn $1 million. Okay? People who are motivated by that have no chance of solving this problem. Okay. Anyway, so why do we care about the Riemann hypothesis? So one reason that's often given is that, well, it gives you a very sharp estimate in the prime number theorem. So error bound in the prime number theorem. So you remember the prime number theorem was the number of primes up to x. It grows the simple version, grows like x over log x. The more sophisticated version is it grows like the integral of 1 over log t from, say, 2 to x. And so the prime number theorem is saying that these expressions, the first one and either the second or third, have a ratio going to 1. You might ask, what about the difference? Just because two things have the same order of growth, ratio goes to 1 doesn't mean that the difference goes to 0. Think about x squared plus x and x squared. Right? So just because they have the same growth rate you can still ask, well, how far apart could they get? So the Riemann hypothesis is equivalent to the statement about how far the integral, not the simpler x over log x, how far apart these expressions can be, and the equivalence is that it should be no more than roughly square root error. The log x is some technical factor that has to be included, but you should think about this. I'm going to write this as c times x to the 1/2 log x. This is for some constant. Any constant would do. For some constant c. That 1/2 there, that's related to the critical line, real part equals 1/2. If you knew that there was a strip a little bit to the left of the line real part equals 1, so we expect all the zeros are on the line real part equals 1/2. But if you start the line real part equals 1, we know there aren't any zeros there. Nobody has ever, as far as we know, has proved that there's no zeros between, well, you can find crank papers on the internet, but we don't have a proof that makes epsilon progress to show that there's no zeros between 1 and 1 minus epsilon of uniform width. People have proved that the zero-free region, grows like this, that gets asymptotically close to the imaginary axis. Okay? But in any case, so even something like that, if you could prove that there's no zeros with real part between 1 and 1 minus epsilon, uniform all the way up and down, that would be dramatic progress, although it would not solve the Riemann hypothesis directly. In any case, so if you can get a strip free of zeros, that width can be transferred into the exponent on the x. And so somehow that 1/2 there is related to the critical line. But this is not the reason that the Riemann hypothesis has this mystique, absent the $1 million, of being such an important thing that we would like to solve. So the significance really is that there's a generalized Riemann hypothesis for many other similar functions. Okay, because it turns out that if you hear that, the Riemann hypothesis implies all kinds of other results that don't even sound like they're related to the zeta function. This error bound in the prime number thing, like where the heck, how is that related to zeros or anything like that? But there are a lot of other famous open problems in mathematics. The Artin primitive root conjecture, for example, you can look that up, that their truth would be a consequence of not this Riemann hypothesis, but an analogous Riemann hypothesis for infinitely many other similar functions. Okay? So the real meaty applications of the Riemann hypothesis really involve using it for infinitely many other similar functions to get your results. So what do I mean by similar functions? Okay, so similar functions to the zeta function. What does that mean? So first of all, they should be represented by a Dirichlet series. These kind of expressions summing a number over n to the s for n equal 1, 2, 3, and so on. So these are called Dirichlet series. So these are analogous to power series, but they have some similar features, but also some more subtle aspects. So to have a representation like this, let's say for the real part, I'll say bigger than 1, or bigger than 2. It depends on the situation. So it should have a representation as a Dirichlet series. It should have an Euler product representation. So somehow it should be a product over the primes of, so the Riemann zeta is 1 minus 1 over p to the s. That should be thought of as a linear denominator in 1 over p to the s. So what you might have instead is other polynomials. The EP of x is maybe some integer polynomial. Okay, a polynomial in 1 over p to the s. Maybe it's a quadratic ending in 1 over p to the 2s, or something like that. Maybe with some bounds you have an E2, E3, these kind of Euler denominators evaluated at 1 over p to the s. They don't all have to be the same expression. 1 over 1 minus x, it all looks the same. But in general, the coefficients might vary with p in some subtle way. But some kind of product representation, reciprocal polynomials in 1 over p to the s, and there should be some analytic continuation to c, maybe a pole at 1, maybe not. And there should be a functional equation relating value at s and 1 minus s after do a suitable normalization. Okay? One can develop some kind of abstract theory. Let's study all functions that have these properties in the abstract and try to verify the Riemann hypothesis. And this idea has never really gone anywhere. But in any case, the point is there are a lot of examples, and we'll see a big class of them in my next lecture, of things that have all these properties. Okay? And we expect, and you can numerically check, that they all fit the Riemann hypothesis up to various heights. And it's the truth of the Riemann hypothesis for all of these, infinitely many at a time, which is where most of the applications of the Riemann hypothesis type idea get used. So with that, I'll finish for today. Thanks.